So welcome to chapter 15. We're going to cover some more details about what happens when you process polymers. And I'll see if we've got enough time to incorporate any of the extra materials. There's a couple visuals that I think would be really helpful for you guys. Big picture, polymers change dramatically when they are processed by comparison to metals. The metals definitely change. There's hardening, there's cold working, there's all sorts of things. Polymers have some additional mechanisms there that aren't present to the same degree for metals. This creates some differences in how we have to actually handle and process those materials. So accordingly, what we want to be doing is we want to be focused on the tensile properties, how those change, what happens with elevated or depressed temperatures, and compare polymer behaviors to ceramics and metals so that we understand what are the actual processes, what are the processing methods, and what effects do those have on our materials. So big picture properties, some polymers are brittle in behavior. So just a little bit so you add stress, they don't move, and then they fracture suddenly, often explosively. This is the case if you've ever dropped a Nerf gun let's see, what is it, humans versus zombies. I know that was going on at campus at one point. I don't know if that's been going on this year. Sort of died at COVID, of course. A lot of interesting and fun activities like Freedom died with that too. So there's that. Plastics sometimes do behave plastic. So those are not synonymous terms, but plastic behavior in terms of stress-strain relationship, those get pulled apart. So with a moderate stress, you get a significant strain forming in the material, and we're going to cover what the mechanism is for this. So the fracture strength of polymers typically is on the order of about 10%, that of metals, so tens of megapascals instead of tens of gigapascals, for instance, or at least a couple gigapascals. You can get somewhere up into the hundreds, I think, of megapascals, but it's less common. So on the order of 10%, and then the deformation of strain in polymers typically is greater than 1,000%. So the polymers typically are stretching and pulling and pulling and stretching to many times their original starting length. And so that means that there are deformations that happen. So a lot of metals and things are typically less than 10%. So this is why we don't build bridges out of polymers at this stage in time, because as you add stress, the bridge would sag and it would be like something out of a Dr. Seuss book, and that would be very bad. Elastomers are the most severe in terms of a little stress gives a lot of strain in the material, so rubbers especially, and other elastomers. So we'll talk about some of the properties of those as well. The brittle cross-linked failing starts with some initial aligning of the chains. They start out as kind of a network, and then near failure, they're a little bit straighter. It's a little hard to tell in this illustration, so they give a little bit better one kind of close up. So these start out kind of compressed. They have a mesh-like network, and as soon as you start pulling on those hexagons start stretching out to become parallel. The more they stretch, the farther or the closer together those parts of the chains get, and eventually they reach a semicrystalline state where they fracture brittly. And so we'll talk about crystalline formation But let's look at the plastic deformation mechanism as well. This one's a pretty important one. There's a zone here where the polymers can be unloaded and reloaded regularly. The brittle materials, they can be loaded and reloaded to an extent, but if you take it up too high, they will fracture and fail. So plastic failure gives you a little more leeway typically. So undeformed structures start with these coiled coils of coils, and you stretch those out. They start elongating, and they are amorphous in nature, really in both cases here, but they're still amorphous. Once you reach sort of this peak, whatever the ultimate tensile strength is for the material, that's where the majority of the chains have aligned, and you've reached a point where now they can't take any more abuse, but they do change dramatically in terms of the strain that's absorbed at that given stress level. So the stress level drops just a little bit as the area changes. You start getting this necking phenomena at this point. So you begin to get block segments ripping and tearing and separating. So this is the beginning of the failure, and then you get a fibrillar structure. So individual fibrous strands are what you end up with left near the actual failure point before it finally detaches, where one of those threads gets thin. That process is referred to as drawing. So you're pulling on both ends of the specimen, same tension test that you guys have done previously. And this is typically something like how a monofilament fishing line is made. So you're pulling and pulling and pulling the material prior to its end use. And that aligns all of those chains in the stretching direction, which results in the elastic modulus increasing in that direction of stretch. You increase the tensile strength in the direction of stretch, and then you decrease the ductility. So they can't take any kind of side loading or anything like that very well. They're not very ductile. They become very brittle, and that's why fishing line snaps instead of just stretches and snaps. It just snaps sort of without warning. Usually with the fish that you can't prove that you caught because it got away because the fishing line snapped, and all you're left with is the wet t-shirt. So annealing is similar in some regards to metal, where you heat up the material, you reverse some of the damage by reversing, or at least some of the effects of drawing. It is damage of a sort to the fibers of the polymer, but also not, depending on what your end use case is. So polymers don't follow the same rules as metals do in regard to especially thin filaments. So reversing the effects of the drawing means it reduces that elastic modulus and the tensile strength, and enhances ductility. So you lose some of those properties that you just did. And that's an interesting thing to discuss in the context of cold working for metals, because there's a lot of things that the metals experience. If you were to feed a sheet through a roller, for instance, annealing brings back ductility, right? It does reduce tensile strength and all of those things, but it's very interesting because the cold working changes the behaviors of the metal in one axis versus the other, such that it now has different kinds of applications. So there's a lot of parallels in that regard to the way that the drawing process and the annealing process work. in comparison to metals. So you can also look at the elastic behavior for elastomers using the brittle behavior for one case. The elastomers are the opposite, right? The brittle materials, you drop them, they fracture immediately and shatter into a zillion pieces. The elastomers, if you have an impact, it just absorbs it, right? Think of like a rubber mallet that just spends its life beating things nearly to death. And just eventually you start peeling off some chunks, but it's very hard to actually destroy a rubber mallet aside from physically cutting it open and snapping the handle off. That's really kind of your two main modes. And the elastomer itself is still just fine, the rubber. So a lot of movement for very little overall stress. That creates some interesting things that happen with elastomers. So the amorphous chains that are kinked and cross-linked behave differently. There's a reason they start out that way, and it has to do with their natural state to want to minimize energy and the fact that they're sort of always in motion. So they're always uneven and curled up into different arrangements. Linking between those stiffens them slightly. The other things that you want to pay attention to are the way that these are behaving as you start pulling tension on them, because without very much movement, they start getting a little bit of deformation, but it's very elastic at this point and reversible. It's reversible basically all the way up until failure, pretty much. At this point, all of the chains are straight relative to each other, or as much as they can be, all cross-linked together. And that alignment puts them into a phase transition where they become crystalline. So they start out with real plastic-like behavior, and then they go into brittle behavior. So that will create all the conditions needed in order for these to work and work pretty well for their specific application. So we'll talk in just a moment about how the mechanism of the change to the semi-crystalline state, how that will result in some differences. We're about to have loud noises in the background. Okay. So these elastomers, as they make this sort of transition through a glass-like state into the aligned state, this is what happens at, for instance, like with tires at the limit of adhesion, where all of a sudden you're pushing the limits all the way up to the limit of adhesion, and then suddenly the tire loses traction, loses grip, and suddenly it's like the vehicle is on marbles, right? It's a very similar sensation to going from pavement suddenly transitioning to black ice. And any of you from a climate where you actually get ice, unlike in Arizona? How fun is that transition to black ice suddenly? Not very, right? All of a sudden, the adhesion properties change dramatically, and you're sort of, to a degree, you're sort of along for the ride, right? And that's very much what this is. You're very much along for the ride when those chains finally break in that crystalline form. They suddenly have the grip properties of like pencil lead, basically, because those crystalline layers just peel off of each other very readily. It's a really huge problem. And that's why it's very hard to control a vehicle at that range. So thermoplastics versus thermosets. Thermoplastics, what these do is they are really the majority of plastics that we use. Not 100% of them, but a good majority of them for sure are the majority of them are liquid first. So they start in a melt phase. They have a little bit of cross-linking, not a ton. They're very ductile. They are these materials that are soft when heated. So a lot of the plastics that you can think of are in this category. Polyethylene, polypropylene, polycarbonate, polystyrene. All of those are examples. Now, you'll probably also know that if you've had styrofoam cups too close to a campfire, polystyrene will return to a liquid state, but that foam turns into a whole lot of foam turns into just a little bit of liquid. And that's something that once you get too far or too close to a heat source, it becomes carbon dioxide instead of liquid polystyrene. So that transition point has to be very carefully managed. That transition point is called a glass transition temperature. So when something goes from being a crystalline solid to being a liquid, starts at the glass transition temperature, then it becomes fully melted, an actual liquid above the TM, the melting temperature. So there's a lot that defines what this is for what plastic. This is just a general phase diagram to give you an idea what's going on. The viscous liquids range is crystalline solid at increasing molecular weights and higher temperatures. So all of those things. Then the partially crystalline solids at higher temperatures and higher molecular weights are mostly at that range rubber. They're really, 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 really tough, long chain polymers. Tough plastics are in this range. So there are a lot of like nylons are typically going to be higher molecular weight in end use. So we have a couple different things that this phase diagram tells us, but we know that the highest range of melting temps typically is rubbers, and this is part of the reason why. For instance, I'm sure there's a video of a redneck burning rubber bushings out of a control arm. You have to really, 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 really work to actually get rubber to liquefy. It really doesn't tend to want to liquefy. It really tends to want to just burn. So that's why liquid is not included here. Vulcanized rubber is actually right here in this category. Vulcanized, so like RTV, room temperature vulcanized, RTV silicone is an example of a thermal set. So this is for thermoplastics, not necessarily thermal sets, but something like rubber, some of those things, phenolic resins, polyester resins, epoxies, right? Once you mix multi-part epoxy, for instance, you don't just like turn it back to liquid or heat it up and it remelts. Like that's just not a thing. Once epoxy cures, it is what it is. It's done, right? So that's an example of a thermoset polymer. Gives off a bunch of heat in the curing process and then stays in its final form. So things like I think a lot of the stuff currently used in billiard balls and things of that nature are in that category. So a lot of those don't tend to melt nicely. So other things are a little bit different, but all the vulcanized versions are not softened when heated. So they become hard, they become brittle, especially over time with oxidation. High degrees of cross-linkings. This is why they can be very stiff. They just don't tend to be very cooperative in a lot of, they don't tend to be cooperative if you need them to return to a liquid state, or they're difficult to remove from things. So that's why we cast rubber feet onto stuff. Rubber feet are really, really durable because they're super duper tough polymers. That's why tires are made out of rubber instead of like cork or something, right? The influence of temperature is important for thermoplastics. So the majority of this whole chapter is really emphasizing properties, changes in properties and processing of thermoplastic materials. So as temperature decreases, the elastic modulus increases, the tensile strength increases, and the ductility decreases. So lower temperature, less and less compliant, and you're going to get very different, more brittle-like behavior out of cold polymers than you are really, really warm polymers. So 60C, which is just barely above outdoor temperature in Phoenix some days, it seems, is a good example where plexiglass, PMMA, gets pretty soft, actually. So significantly different tensile strength, especially if you think about the laminated plexiglass or something that goes into something like, we won't call them bulletproof glass because that's a misnomer. It's neither bulletproof nor is it glass. It's actually laminate layers, many layers of typically a variation of high molecular weight plexiglass. Those at elevated temperatures are more compliant than they would be at lower temperatures. So at lower temperatures, it takes a lot higher force to be able to actually deform them. Increasing the strain rate has the same kind of effects. So plexiglass can take a hit typically pretty well. It's pretty tough stuff. If you were to put it in tension and pull it really fast, it would not do very well in that particular environment because of the combination of ductility and tensile strength that specifically it has. So a little bit more quickly about this melting temp versus the glass transition temp. Melting temp and glass transition are dependent on chain stiffness, and that increases with the presence of bulky side groups. So if you think about some of the networks that we were looking at earlier, if you have a bunch of partially cross-linked polymers that have a lot of branching and those branches interact, anytime you've tried to like move a pile of branches from one place to another, you try and pick one out of the group and all of the rest of them get stuck and you have to sort of pick up a big bulk. That's the same kind of behaviors that polymers tend to have, but at a very micro scale. So the chain stiffness is increased by all these side groups, by polar groups and side groups. So this is something that biological molecules take advantage of: disulfide bonding, polar bonding between these different polymer chains in order to bind things temporarily or for such and such an energy change. Really, really stupid efficient in terms of energy use. Very impressive system in terms of energy management. This is why some of the best engineering ultimately ends up approximating things that are already present in biology. which should tell you something about the design behind biology. So the chains and the double bonds and aromatic chain groups dramatically increase stiffness as well. So remember the structure for polycarbonate, where we have a couple benz rings in the chain of the polymer itself. Those don't want to flex and bend and move. They want to sort of stay the way that they are. And that means that the material is going to behave more like a crystalline solid. So it's going to be more linear in its behavior. As soon as that transitions across the glass transition temp, looking at 3 different examples, assuming they had the same glass transition temp, this is what they would look like, where glass is liquid above a certain range. At the glass transition temperature, the behavior of glass becomes very, very different. So it starts to expand very quickly relative to its original volume. Semicrystalline solids, not nearly as dramatic a change. And then crystalline solids, almost linear in the way that they work. So if you were to imagine heating a block of salt or something, a crystalline solid, even ionic bonded like that, is not going to change dramatically with temperature. So you're not going to like melt down and liquefy quartz, right? Like that's not really a thing. So the crystalline solids behave very linearly with temperature. Semicrystalline solids do not. So another thing that affects it is the regularity of the repeat unit. So if you wanted to alter the way that a polymer was behaving in a bulk phase, this is where you might use or take advantage of the bulk properties of 2 different kinds of polymers and connect them together in a block copolymer, such that you could have some intermediate, something to temper the melting temp or increase or decrease the glass transition temp, or make it more compliant, more hydrophobic, less hydrophobic. There's a lot of different approaches that you could take to this in order to change some of these kinds of properties. Another thing that's important to understand from this is the concept of a stress relaxation test. So strain in tension to some epsilon naught, some given strain, and then you leave it there. Over time, the actual stress goes down. So the stress level, even though the sample is physically pulled and stretched to the same degree, it hasn't changed. It's not moving. It's not changing size and shape. With time, polymers, specifically thermoset polymers, relax, meaning they equalize or distribute those stresses across the entirety of the chains. And that's why the measured stress goes down, but the sample stays in the same spot, because it's always trying to equalize loads and stresses. That's something that polymers do quite a bit differently than metals do, where metals just sit there at the same stress and go, okay. They don't actually have any additional interaction. So that expression looks like stress as a function of time divided by epsilon naught. So there's some time-dependent function. For a large decrease in the relaxation modulus, what we see is at temperatures above the glass transition temperature, you go from kind of the normal solid crystalline state into a transition region before becoming a viscous liquid. So the transition region is where you get flow So it's not melting. It's not necessarily cold flow, but it is in the sense that it's below the melting temp. And so you get flow in polymers. The original glass that was used in a lot of the ancient world, for instance, they didn't have some of the things we have today, where the plate glass they made in the ancient world, they would have a cold flow issue where the glass, under just the force of gravity, all of the molecules would slowly flow to the bottom. So a lot of the stained glass windows and things of that nature are thinner at the top and heavier at the bottom, and thicker, measurably thicker at the bottom than at the top, because of that property of the glass being crystalline but not rigidly crystalline. So there is some room for flow. When you add in different additives, you change some of those properties, and you do the same thing for polymers. So some example glass transition temperatures for low density polyethylene versus high density is something like -110 and -90. I half wonder if those are typos, but what that's telling you is their glass transitions are significantly lower than something like PVC or polystyrene. So that's the reason that polystyrene foams, as an example, are not able to withstand boiling for very long. So if you leave a polystyrene cup in the microwave for an extended period of time, with water trying to boil, it will deform the polystyrene and create a big mess. And if you're really lucky, it'll even catch fire inside the microwave when all the water spills out. So that definitely doesn't happen sometimes. Definitely not a true story from the faculty lounge, and no, it was not me. They were shamed for many moons after that. Polycarbonate is one that has a much higher glass transition temperature. So you have to have it hit 150 C before there's any discussion of actually having that transition into a flowing state. So a good application to use to explain that would be the clear plastic measuring cups and things of that nature. More often than not, those are going to be polycarbonate because of the higher temperature tolerance, but they also tend to be more brittle. So with extreme thermal swings, the likes of which can happen in a dishwasher with cold water and a hot heating element or something, those have a tendency to form cracks, especially right at the point where the sprue is cut off of the base for the injection mold, usually at the center. So that's why they tend to have a star crack out from the center. Yeah, question? Or you just fell asleep on your keyboard. It's always hard to tell, because that definitely never doesn't happen. Okay, well, we'll keep an eye out for a question. So polycarbonate is an important one. This one, there's a test that the METs are going to do this week that probably would benefit you guys to be able to see, but we don't do a lot of tensile testing with the ABS dog bones currently. So that's something that probably needs to improve. One of the things that we can focus on is the way that the fractures actually happen. So crazing is this thing that happens in the plastic where you have microvoids form and you have fibrillar bridges form between those microvoids. And it basically allows the polymer to sort of unzip from one side to the other. And that's very much the mechanism of failure. It starts wherever it gets weakest, wherever they get farthest apart, and then the stress on the next one increases and so on until there's no more fibrillar bridges left and they're separated. There are two types of polymerization. So this is partly a review of what we covered yesterday, but also partly covering a new technique. So the free radical polymerization we saw, and of course by yesterday, I mean Friday, whatever it was, a week ago, essentially. Initiation, a radical comes in, throws stuff around, goes all Rambo on the double bonds, creates new radicals. All the radicals get together and gang up until two radicals meet in the middle and they both kill each other. And then there's no more radicals. The only thing left are moderates. And then we have our polymers and there's no more propagation. Then we have termination is typically what that's called. So that's typical chain addition, usually by radical polymerization. Condensation, what we have is a little bit different. We have a hydroxyl and a slightly acidic proton get together, form water, and leave behind very often something like an amine. And we get a polymer, so something like adipic acid and hexamethylene diamine. So two amines, NH2s, next to a carbon, come together with the acid. So something that is, or this is a, this is an acid. It actually functions in this case sort of like a base to donate a hydroxyl group. So that can be a little bit confusing, but it's essentially an acid-base type reaction. And something like nylon 6,6 is formed as a result of this. So again, 6 carbons on the left of the amine, 6 carbons on the right of the amine is where that comes from. So this can alter not only the properties, but the processability and the durability of the materials. There's a bunch of fillers that are used. That's to change abrasion resistance, toughness, to decrease cost, etc. Carbon black is one of the most common by far. It's usually what's used to color or pigment something to the black side. Silica gel is another common one used for lots of different reasons, including kind of trying to make things lightweight, trying to make things more temperature tolerant, all of those sorts of things. Wood flour, which is a really fancy way of saying finely ground sawdust. So think MDF before it becomes MDF. Not like big chunks that go in fiberboard, which is probably the worst construction material there is. But it serves its purpose. Flour, so wood flour is fancy sawdust. Glass, limestone, talc, all of those sorts of things can be added in to change the properties. In the case of talc, they're typically looking for something that's low cost. Plasticizers. So this is a big one, especially for the crunchy stay-at-home crowd that really don't want any BPAs in any of their things. Bisphenol A is an example of a plasticizer. So it's something that helps reduce the glass transition temperature such that it allows for lower temperature molding of things instead of higher temperature. So they transform what would otherwise be a brittle polymer into a ductile one. And there's a couple reasons for that, especially for something like PVC, in order to make it less brittle. PVC is already very brittle as it is, but in order to make it less brittle, they add plasticizers to it, as the name implies, to help them behave more plastic-like. So even though they're already plastics, that can be a little confusing. Antioxidants and UV protectants are also examples. So UV protectants, especially the lubricants. This is very common for a polymer material where it's going to be used for something like a bushing-like or bearing-like surface. So there's a lot of examples of how that might work. You're adding these to improve the way that they move through a dye, for instance. Sodium stearate is an example of that. Also, sodium stearate and a couple other stearates are used in different kinds of beauty products and skincare products for some of the same reasons, to make them feel more slick, even some of the natural derived ones, to make them more slick, to feel more like ones that have higher level of silicon and artificial compounds in them. So sodium stearate is an example of that. It adds a kind of a creamy lubricity to the materials to make them much more slick for the processing purposes. Colorants, dyes, pigments, that part's pretty self-explanatory, but flame retardants such as chlorine, fluorine, and boron. Fluorine, we talked about a little bit last time. Fluorine is pretty savage in terms of it doesn't want to react with really anything else. It could care less. To get it to react, you sort of have to either start with something like hydrofluoric acid, or which is like extremely dangerous. Basically, don't ever get anywhere near it. Or you have to really heat the crap out of it to get enough energy in order for it to react. Boron is similar in some ways. So thermoplastics are cooled and reheated, and they can be recycled more easily because of it. They need to be heated until soft, shaped as desired, and then cooled. So that's why we like to do all sorts of molds with them. They are very compliant that way. Polyethylene, polypropylene, polystyrene are all some of those, but thermal set polymers, they form a molecular network and they degrade rather than melt when they're heated. And when they're molded, typically they have a pre-polymer molded into a specific shape, and then they have a chemical reaction occur to polymerize it. So urethane or epoxy are good examples of that, right? If you've ever tried to repair a car bumper in probably anything sort of 2005s and after, almost all of those parts are all urethane now. And it's really not easy to do a melt-based repair, because those really don't like to melt down. They like to burn. They don't like to melt down. So it's really hard to do any kind of repairs on those, and that's part of the reason why they typically are just replaced. So they work well in their application. They hold up well. They're durable. Once they're destroyed, it's very hard to get them to come back. So thermoplastics and thermosets alike are processed by molding. This is very easy on the molds. They can do tens of thousands of units off of a single mold when they're set up correctly. When that isn't the case any longer is when you start getting like fiber filled polymers, and those are actually really, really aggressive. And one of the things that I got to see from some of the experimentation I did with those in additive manufacturing was just how quickly even something like uh, I think I had seen something like a stainless steel nozzle being used for some fibrous filler material, and the process of the nozzle sweeping across the surface was enough to literally sand off with all of those rough fibers. It was enough to sand off like 80 grit sandpaper to reduce the amount of nozzle that was there. So it reduced the height of the nozzle. It was pretty wild. So very, very aggressive polymers that are abrasive, and you have to have really high hardness of your molds in order to get a lot of molds out of them. So they have to throw them away and replace them, the molds, after just a number of applications. So it's in the, I think, single digit thousands often. Um, so materials like brass would never survive as a mold for that. So the molds are typically heated, then pressure is applied. You have alignment dowels. You have the platens, which are actually enforcing the pressure distribution. So that sets the end force that's being applied. The fluid polymer assumes the shape of the mold as soon as everything is pressed together between the mold base and the upper portion of the mold. So another example is extrusion. So this is closer to, in principle, what some of like the 3D printers are doing. They're using thermoplastics. They aren't using ram and a hopper. That's very much more the way that professional extrusion is done. So you use the ram to fill the plastic pellets into the area, into the chamber area for heating. And then you move the material through down into a nozzle that is shaped for your end application. So this is very commonly the way that a lot of filaments, for instance, are made. A lot of plastic filament types are in this category. So there's always a force injecting this into the mold. So the ram is actually displacing the volume required to fill the mold. Anyone know why they have a spreader in the middle? What would you guys guess? Why would they want to have some sort of spreader in the middle and force all of those pellets around it? This is not free floating in space. It's anchored on one side. Can anyone hazard a guess? How about for heat distribution? So if you want these to melt evenly, if you just shove it into the middle and hope that it melts all the way through, you have an uneven distribution of temperatures throughout. So you have inconsistency in your polymer. Whereas if the ram shoves the pellets up around on either side, then they're going to get heated more evenly because this is going to stay warmer and the sidewalls are going to be very warm because of the heating barrel. And that's what allows you to consistently push material past and fill a mold. And the size of that spreader is probably calibrated for an injection range up to a certain point that it can inject continuously, or a certain volume typically. And as soon as that molten liquid is filled into the mold, it'll assume the shape of that mold. So this type is often used for generating filaments. So you have pellets, you have a feed hopper, and you have a screw extrusion method. You have barrel band heaters, and you have a shaping die at the very end that's typically removable and swappable. And what you do is you feed the material into the hopper, you melt it using the heat from these bands, and then you continuously rotate the extrusion screw to move material from one end to another. And the extrudate that comes out turns into whatever your end product is. If you add air to that and rotate it 90 degrees, what you do is you create an air bubble inside that polymer. So you get the blown film. This is the same way that a lot of the packaging is made for cereal boxes, for Ziploc bags, Walmart bags, a lot of those sorts of things. Air bubble method is what they're starting from. So there's a lot of applications that use this kind of methodology, and that's how they do it. There are some fibers as well that come out of the general family of polymers. So those are usually much longer length to diameter ratio. So over 100, it's considered a fiber. Typically, that's used in variations of textiles, so all kinds of fabrics. They need to have high tensile strengths. They need to typically have a high degree of crystallinity. And then sometimes they'll have a lot of polar groups, and that's part of the reason why it can be so hard sometimes to get things like tomato stains out of clothing, because they form a pretty effective bond. Usually these are spun. So they extrude a polymer through a spinneret, which is a die that has many small orifices, and that spun filament is drawn under tension, leading to highly aligned chains and a fibrillar type structure. So these can also be used in coatings, so thin polymer films applied to surfaces, paints and varnishes, things of that nature, protecting from corrosion and degradation. They improve the appearance of things, and then they can provide electrical insulation. Sometimes you want to turn them into adhesives. So there are a really wide range of these that are adhesives, and they bind with a couple different mechanisms. So van der Waals forces, and then actual mechanical grip by way of penetration into the pores and crevices that are involved in that particular bond type. So think about like how you would stick something to a concrete cinder block where there's all these voids and there's all this empty space on the very surface. There's a lot that goes into that. Films are important as well as foams, because that's something that has come a significant way in the last about 30 years is foams. So not only like the fire retardant foams and things that they're using now, but also when making mattresses, all sorts of things. There's factories all over the place who are designing materials out of foams. So foam mattresses were not a thing really. Maybe even about 20 years ago, foam mattresses were, at least all foam mattresses, were pretty rare. There was foam in and involved with mattresses, but I predate foam mattresses too. So not just Google and the internet as you know it, not just cell phones or the third dimension. I'm basically ancient news by that standard. Medical implants are another big one. So things like ultra high molecular weight polyethylene. It's a good example. Molecular weight of about 4 times 10 to the 6 gram per mole is there. So there are some really, really great properties to leverage. And there are things that are available that are made of that material. Some common items, but they're used very heavily in like medical applications, things where you need high impact strength, you need resistance to wear and abrasion, you need low friction coefficient on the surface, and self lubrication. Because if you think about having something like a hip replaced, if you get up in the morning and there's all sorts of grit and things in that cup, and you have a grinding or squeaking sensation, that would be really awful, and people would complain and it would be bad. So you need really, really tough, high-tech materials, very demanding, have to be very uniform, have to be very monodisperse in order to do the job that they are designed to do. So there's other applications like, again, we'll say bullet resistant vests. Bulletproof is, there's always a bigger bullet. So bulletproof is very much a misnomer. Golf ball covers, those are particularly hard polymers, and hip implants are some other cases for those. So the ultra high molecular weight polyethylene is used in some of those as well. So a lot of along with ballistic nylon to contain all of the parts on the outside. Advanced polymers are typically combining these hard component domains. So typically something like block polymers and shock absorbing or soft compliant domains. So different regions by changing the ratios of those. Something like butadiene, so styrene, butadiene is a good example. So that bends ring, very inflexible. Butadiene, just a double bond. So a little bit of flex, but not much. And then very inflexible in the case of the styrene when it's highly polymerized. Those are all examples of things that we want to be able to tune for different kinds of properties. So some of the biggest limitations are these values are typically pretty small. There is a time and temperature dependence in the deformation. So the thermoplastics, The examples we went over: polyethylene, polystyrene, polypropylene, polycarbonate, typically are lower on the elastic modulus. They're lower on the ultimate tensile strength or the yield strength, and then their application temperatures tend to be lower than thermal set polymers. So larger components, things that are easier to form, and they're easier to form and recycle. Elastomers are a pretty big percentage also of the things that we use. We use them because of the reversible strains. It's really convenient to be able to store those energies, especially if you need to be able to store up energy on dozens of rubber bands to help, keep classmates awake or something like that. There's a lot of creative uses of that reversible strain in the elastomers. Thermal sets are important for a lot of reasons, and it includes things like epoxies and polyesters. There are materials like the polyethylene terephthalate that's used in a lot of drink bottles, things like that, that are currently being recycled into new printing filaments and things. Those are not the highest quality in terms of end product, but I guess if you're in a total fallout situation, then you'll have to be working with what you can in order to make stuff. So can be done, not necessarily ideal, because polyesters tend to be more on the thermal set side. In the case of printers, they're glycolated a little bit, so they add glycol into the polymer to allow for, again, lower glass transition temperature, slightly lower melting temperature, so they're easier to work with in a lower temperature setting. So compression and injection molding, extrusion and blown film extrusion are very, very commonly used. So things that, like, you couldn't do a blown film extrusion with like lead, that would not be a thing. All you would have would be a mess. So there are things polymers can do by stretching and taking some of this energy that other materials just can't do, and that's why we need them. So they also have the melting and glass transition temperatures that are dependent on what end case they're actually using. So even in the example that I saw just last night of a machine that was making nails or something like that, they were coating those nails in a thin film to prevent oxidation and rust so that they could be used in outdoor applications in nail guns. So it's always about trying to use an advanced material or technique to accomplish a goal. And then foams have come a long way. Those have become really, really important, especially in automotive manufacturing, to have foams be lightweight but strong, but also somehow soft to the touch. So all of the, like, 12-year-old whiners that are all the car reviewers don't complain about, this feels like cheap plastic versus an expensive plastic that's the same material. Sure thing, here's your sign. A lot of those foams are actually very high-tech materials now because they also want them to be, in some instances, things like fire retardant, so that people have a longer time to be able to get out of the vehicle in case of something like an electrical fire. So there's all of these things going on behind the scenes, aside from inflation and the total destruction of our monetary system, that are why cars are much more expensive now than they were 20 years ago. Like 10 times more expensive, literally. So whoever's doing the inflation numbers and calculating, 6% per year, really can't math. Because when something is 3 to 5 times more expensive, 6% doesn't get you there. without like 30 years of time. So fun facts, you got to be able to math to be able to do life very well. All right, we are just about out of time, and you guys are probably just about turned completely to mush. It's a lot of material, but any questions on this? Probably half of you are afraid to note that you left the call because of falling asleep or dropping your phone, all of those sorts of things. If there are questions, I'll try and keep an eye out. There's a lot of projects and things still going on. I'm in the process of working on putting the final together because we have to have students taking that starting on Monday. I'm going to try and get you guys through the last of the materials by Friday so that we can get you guys all set. I'm going to double check the due dates for a couple things. You're really going to need a couple things in terms of equation sheets, things like that. So I'll get some of that posted, but I need to verify that we have enough time to actually get things like the homeworks done, because we have the homeworks and the final, and I think finishing the website projects all at the same time, and then a bunch of students trying to get on planes and leave on Friday. So it's a mess. So I'm going to try and have you guys through everything by Wednesday. We'll give it our best shot.